Benjamin Martinez, and today we'll be drawing the hybrid orbital of carbon monoxide. So before we begin, we should break down what is carbon monoxide. So we have carbon, and one oxygen. And so first we should get our valence electrons so that we can create our Lewis dot structure. So carbon has 4 valence electrons and oxygen has 6 valence electrons. And since we only have 1 carbon and 1 oxygen, we could just add these directly together to get 10 valence electrons. So now that we have our valence electrons, let's create our Lewis dot structure. So our most simplest Lewis dot structure would be adding 6 electrons and creating a single bond and adding 2 electrons to carbon. But this would not be the best Lewis dot structure when we do our formal charges. So we move on and we take a pair of electrons and we move it into and add a double bond. So then we can go to C double bond O with 4 electrons on this oxygen and 2 electrons on this carbon. And to break down what I said earlier about the formal charges, let's just do the formal charge real quick for oxygen. So oxygen is, again, like I said earlier, has 6 electrons, valence electrons. And then we have 1 bond minus 6 electrons on the thing, on this currently. So that gives us -1. And if we did the same for carbon, so this was oxygen, let's do the same for carbon. We have, I believe it is 4 valence electrons with carbon. It has 1 bond minus 2 equals 1. So this would be negative and positive. This is not the best that we can get it at. We can get it to 0, so let's try to get it to 0. So for this one, the formal charges for this one that we have here, let's just write this as number 2. The formal charges for here would be, let's do oxygen first again. So we have 6 minus 2 minus 4 equals 0. So this would be 0. And then let's do the formal charge for carbon. So carbon would be 4 minus 2 equals 0. Okay, so this one, let me make sure. Yeah, so this would also be 0, but we could still go further because we need to obey the octet rule with both of these. So because carbon and oxygen both obey the octet rule despite the formal charges, we still need to go and push this further. So let's go and take one of these bonds and move them in to make a triple bond. And to recall everything I've just explained, the octet rule is that each one of these O and C need to have 8 electrons. So currently this O has 2, 4, 6, 8. So the O is fine with the octet rule, but the C has 2, 4, 6. So we could fix that. So let's move in this and make this a triple bond. Now we have 2 electrons on each. Now it's 2, 4, 6, 8 for the carbon and 2, 4, 6, 8 for the oxygen. If we do the formal charges, it would be 6 minus 3 minus 2 equals 1. And this is for oxygen. And C would be 4 minus 3 minus 2 equals -1. And yes, they're not 0, but because these obey the octet rule, we must go with the configuration for the octet rule. And so now we move on to our next step, which will be assembling the hybrid orbitals. So what we do from here is we do S, P, P, P. And so if we look back here, one of these the initial one creates a sigma bond, and these 2 separate double bonds create pi bonds. And we can take these pi bonds that we made from this triple bond, and we could take off 2. We could cover our thumb. We can grab our thumb. Let me put this, and take 2 away from here, and that leaves us with S and P. And so now that we have, mind you, so let me retrace. These pi bonds will subtract from these p orbitals and take it away, and we're left with S and P. So whenever we create our structure down here, let's do CO. We're going to do 2 peanuts. Let's do a peanut here, and peanut here, or as they call them in the homework, dumbbells. So we have our dumbbells here. These 2 dumbbells here create a sigma bond. And let me actually move this a little bit lower so we can have a little bit more room to work with. And then we create a, let me change the color, a vertical dumbbell here, here, here. And this creates one of our pi bonds that we have with our triple bond. And now we still need to create one more pi bond. So let me switch to orange. So we will do one that is kind of like, it's on the axis technically, but it is in a way vertical but on a different axis. So we will do it like this as well, and let's bring this down here as well. And these will create lines similar to this one here, but since they're vertical, we're going to just dot them. So this one would go here, and this one would go here. And these would create our other pi bond that we're looking for, okay? And so the importance of what we did earlier is we have an S bond, so we have our, so now that we have our hybrid orbital structure here, we have our pi bond on the bottom, and we have a pi bond on top that is a vertical pi, well, a horizontal connection, but a vertical dumbbell. And then our bottom pi bond that we have here is a dumbbell that is on an axis at a different angle, but still considered vertical to an extent. And then we of course have our sigma bond in the middle. And now that we have these, we can create our structure. So let's create a structure for this. So we would go one here, and this will be given on the test, so we don't necessarily have to memorize this, but it will help. And then we have one here. Okay, so let's just create this as our box right here. And 1, 2, 3, 1, 2, 3, 1, 2. Okay, so let's do our outside electrons. So we knew that when we counted the valence electrons for carbon monoxide, we had 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and this side is oxygen and this side is carbon. Let's do the inside now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have 10 in the inside and we have 10 on the outside. And now you're probably asking, why is this C not a double bond? Why didn't we fix it like how we did the O's on the right side? Okay, so the O is higher in electronegativity, because if we look on our periodic table, O is further to the right than C is. So that for that reason, it is given more lone pairs than C, because it's necessarily a bigger bond, but altogether C and O equal up to 10 electrons as we see in the inside. Now that we have that kind of sorted out, we can move on to figuring out if this is a diametic or a paramagnetic structure. So to figure out if it's a diametic structure or a paramagnetic structure, let me write those right here. Para and dia, mag, I don't have space, but paramagnetic and diamagnetic. So paramagnetic, what we were told in class is to not think of paramagnetic as pairs. Think of it as a single by itself. So this structure, I'll just say it here, is a diamagnetic structure internally. Internally is a diametric structure because it is fully even. You can always think if it's an even valence electrons, it'll always be diamagnetic. To an extent, we could always just automatically assume that when we fill out this structure here, it will just always equal out to both of them having a lone pair alongside it. And we can look at that just by internally. So let's look at this here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that because it is even on the inside and each one of these has a pair associated with each other, it is diametric. If we look on the outside, so let's say one of these lone pairs was taken away, we can rule that this would be a paramagnetic structure. But it is not, so we will go with it being a diametric structure, meaning 2. We can think of di as 2. The next thing I kind of want to bring up and mention is that when we're doing these, let's just bring up whatever. It doesn't have to be one that we've seen before. But when we do these, we want to fill them out like filling out with one pair, then the other pair, and then we go back and fill them up and go back and fill them up because we don't want to fill them up like this first and then this side because it wouldn't evenly disperse our pairs correctly. And if it was an odd number, this would possibly mess it up in us thinking that it is a diametric structure when in reality it could be a paramagnetic structure, leaving something out. Like for instance, if it was 3, I can't think of one that would be 3 off the top of my head, but we could even say if it was 9. But for instance, this is going to be 3, so we would go here and we'd fill up this one, and then we go back and fill up this one, and then boom, we have one left here. So that would mean a paramagnetic structure. Probably overcomplicating this, but this is the correct hybrid orbital for carbon monoxide, or CO. We've gone through all the steps. We'll go to my next problem now, where we will be discussing how to figure out, honestly, I completely forgot what the next extra credit question was, but we'll be figuring that out right now. Credit. All right, guys. So sadly, my audio cut out, so I'm gonna have to do this just off of watching my video and going over it. So now let's start off with our 2 polyprotic oxyacid fluid dot structure. So we're gonna be doing HCO3 negative to begin with. So let's first do our valence electrons here. So we have H, C, and O. And so we know that because we have the O3, that 3 is going to be next to this O. And we have C and we have H there. And we know that because it's just one H and one C, we're just going to do 1 times 1, which 1 and the 4 and the 6 is what we get from our periodic table. That gives us 1, 4, and 18 when we multiply those together to get 24 valence electrons. If you're asking where do we get that plus 1 from, we got it from that negative in HCO3 negative. All right, so now we have our valence electrons. We can start creating our Lewis dot structure. So we put our C as our central atom because it is the least electronegative. We have our O's on the outside, and we have our H right next to a random O, but just that O in specific, just because it looks the best, I guess, in my eyes. So now let's start adding our valence electrons. So we have 4 currently on the O, so let's add 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24. There we go. We have 24 electrons now. But this C does not obey the octant rule, so we do have to fix that. So we're going to be moving one of our O's. There we're going to be moving one of these O's into there to create our double bond, so we can obey the octant rule for C. So let me just wait. I'm going to redraw this here. And the O on the right will stay the same, as that one already obeys the octant rule. The H doesn't have to obey the octant rule. And so now that we have this process here done, we're going to see, so it looks like they all obey the octant rule. And we can start doing our resonance 1, 2, 3 method that we have been taught in class to see which one is the best. We could also start doing our formal charges once this is done. So the 2 and the 3 is always going to be in between a double bond, so that will always help you when you're doing these 1, 2, 3 methods. So we're going to grab that double bond and place it on that bottom oxygen. And we're going to take the first for our number 1. For 1, we're going to take one of the paired bonds and move it to and create a double bond. So it's pretty much just a flip of everything for this specific HCO3 negative. And so it will be what I'm writing down right here. Yeah, man, this really sucks that my audio cut out. It's a lot more difficult to do just by watching me write in complete silence. But we could do the 1, 2, 3 method here, and that would just give us exactly what we just did on our left side. And what we can do next will be our formal charges. A little bit of the screen's a little bit cut out, but I'll most likely drag it down, hopefully. If not, I'll have to fix that in post editing. But we start doing our formal charges just to see which one is the best. So we can do O. I'll just do it off the top of my head. The bottom O will be -1. And the top one will be, so 6 minus 2 bonds minus the 4 electrons on it. 6 minus 2 is 0. So the top O will be 0. The right O will be 6 minus 1 minus 4. That's left with 1. Make sure that I write 6 minus 2 minus 4. It's actually supposed to be 0. I accidentally misdid that one, but that's supposed to be 0. That where the 3 is supposed to be 0. So where that 3 circle is, that one is 0. 6 minus 1 minus 4. Yep, that's 1. So everything else looks about right. That C would be 4 minus 3 minus 0, so 1. All right, so this would be its best, most happiest state, where it's at its best. This is the most we can do with resonance for HCO3 negative. But when we go on to our next one, this is a little bit better example, a little bit harder one, where we have multiple different structures that we have to do and multiple different steps to find our best Lewis dot structure. And we have 2 agreeable Lewis dot structures after resonance that give us good, like, we can use both of them basically. So yeah, let's move on to our next one. So we have, give it a little bit of time, give about 10 seconds so I can hopefully get on track with the time according to my iPad, watching the video on here and then talking over it. So for our next one, we have N and O. So N and O, let's do our valence electrons here. So we have N, and then we have 2 N. So N is 5 valence electrons according to our periodic table. So we have 5 times 1 for those N's, and then 6 times 1, which would give us 16 valence electrons. You can just do that, write down 5 plus 5 plus 6. So let's start creating our Lewis dot structure. So we have N, O, and an N. N is going to be our central atom because it is the least electronegative compared to O. And we're going to have to put our 16 valence electrons. We have 6 on O, 6 on N. But we can see here, even though this adds up to 16, 6, 12, yep, 14, 16, even though this adds up to 16 valence electrons, this is not obeying the octant rule. So we would have to fix this to obey the octant rule. So let's move one of those lone pairs inside and create a double bond on N. And that gives us still not obeying the octant rule. Despite the outer atoms obeying it, the inner central atom is still not obeying the octant rule. So we'd have to fix it again. So let's steal one of those lone pairs from O, move them in, and create a double bond. So we have N double bond O, double bond to the N. And now this obeys the oxidant rule. And we will later be doing the formal charge on this one. I don't know if I do it right here. Oh, I do it right here. The formal charge. So we have N, N, O. So we can do our number. Our top N will be our central atom. The other one will be our left atom. And the O, of course, is the only O, which is our right atom. And so we have 5, according to our periodic table, valence electrons in N. We have 4 bonds connected to that central atom, minus 0 lone pairs. So 5 minus 4 minus 0 equals 1. I was just demonstrating what it would be like if there's a lone pair. We would add the 1, but it is 1, and it's actually positive 1. I fix it later, but it's positive 1. And then in the one on the left, it's 5 minus 2 bonds, minus 4 electrons, which is negative 1. And then the other one is 6 minus 2 minus 4. Going a little bit ahead of myself on the video here that I'm watching, but that is 0. Okay, so this one is technically considered a good enough Lewis dot structure, but I will be showing us a better one that to me looks it's the same, but better. So let's go on to our next one. So we're going to be doing our 1, 2, 3 method. We're going to be stealing a lone pair from this N, moving it in to make a triple bond, stealing a bond from N to O and putting a lone pair on O, making it 6 electrons on O. So 2 triple bond N, bond O, 6 electrons. And we're going to do our formal charge here. So our central atom would be 5 minus 4 minus 0, which is 1 again. Our left nitrogen will be 5 minus 3 minus 2, which is 0. And our oxygen will be 6 minus 1 minus 6, negative 1. And I am going a little bit ahead of myself just because I've done this pretty fast, but in my video I'm probably a little bit behind. But this one is the best because we leave the negative on the O. And O being the bigger in electronegativity, the bigger number going right on the periodic table, we want the negative to be on the O in every circumstance, okay? So because of that, this Lewis dot structure is our best. And here's me writing the 1, 2, 3 method because I forgot to write them down. But this resonance structure is the best. And I'll go on to show a different example where we do it in the opposite direction, where the 3 is the 1 and then where the 1 is the 3, just to show why that one isn't considered the best. So I just do it real quickly here. So I do N, single bond N, triple bond O, and just flip the numbers, and I'll quickly do the formal, why am I blanking? Formal concentration, is that? We'll do the formal concentration. I believe that's what it's called. I don't know why I'm blanking on that name first. Formal charge, not formal concentration. We'll do the formal charge. So our central atom N is N, so 5 minus 4 minus 0, so it stays 1. Our left nitrogen is 5 minus 1 minus 6. 5 minus 1, 4 minus 6, negative 2. And then our oxygen will be 6 minus 3 minus 2, which is 1. Let me just let my video catch up. And if we put these numbers into our Lewis dot structure, we could see that not only is our central atom not 0 or close to 0. I mean, none of these are really, but these other charges that we're getting are so far apart from getting close to 0. And the O is also not negative, it is positive. And that's what makes this bottom one not right, our middle one the best, and our second one somewhat okay, just not the best. It's at its happiest when it's at the one that I have checked. And that's all, guys. Thank you for watching. Everybody have an amazing test and do great, hopefully. And yeah, gonna be doing my TikToks now for the extra credit.